Very soon, we're going to learn an amazing way to go about computing these definite integrals that doesn't use any amount of geometry but uses really powerful calculus techniques. If this video is a review for you, the theorem that I'm talking about is the Fundamental Theorem of Calculus, and it relates concepts of area to concepts of antiderivatives. And so it's this really powerful technique for finding values to attribute to these definite integrals. However, what I want you to keep in mind is that because of the way that we've defined definite integrals, there is always theoretically an option to compute the values of these definite integrals using geometric techniques. And it's really important to remember that we have this tool because there are times when the tools of calculus are not always the best tools for the job. So if you have seen the Fundamental Theorem of Calculus before, and if you are comfortable computing antiderivatives, you may find yourself a little perplexed when you look at this integrand. It's not actually very easy to find an antiderivative for this function. It's quite difficult, in fact. But what I would like to do in this example is to show you how to go about finding the value of this definite integral with geometric techniques. And really, finding the answer is quite simple once you remember to use geometry. Generally, geometry goes a whole lot better when we have a picture of something. So the very first step we're going to take is to draw a picture of our function on our region. This definite integral from 0 to 4 of this particular function, the function is what I have plotted in red here. And what we want to do is find the area between this curve, f of x, and the positive x-axis between 0 and 4. So the shape that we're looking for is the one that I'm tracing right now. There, all the way up to here, down the function, and back down again. So we start by drawing that picture and identifying the region that we need to find the area of. The next thing we do is identify the common geometric shapes that we see in our picture. Now it's very important here to realize that just as calculus isn't a perfect tool for every definite integral problem, neither is geometry a perfect tool for every definite integral problem. And so if we want to use geometric shapes to get an exact calculation on this value, we'll need to be sure that we really and truly have geometric shapes. The first shape that I've identified right here is this rectangle, and that green area is denoting sort of the difference between where our shape and our function ends up here and the positive x-axis. I feel very comfortable that that shape is a rectangle. This shape up here looks kind of like a quarter of a circle, but I want to be absolutely certain that that shape really is a quarter of a circle. And for that, what I'm going to focus on is looking at just this part. This +3, again, is the shift that we've identified here, the 3 units that we've gone up before we start drawing this part of the function. So ignoring the +3 and focusing just on the square root of 16 minus x squared part, if that were equal to our y value, then squaring both sides of that equation and adding x squared to both sides of the equation would give us this equation, x squared plus y squared is equal to 16. And it's in this form that I recognize this as the common or standard form for a circle of radius 4 centered at the origin. So what that +3 does right over here is shifts that circle up 3 units. So I should be graphing a circle of radius 4 centered at the point 0, 3. So indeed, this portion, the square root of 16 minus x squared part that's right up here, is in fact a quarter of a circle. And once I'm positive that that region just doesn't sort of look circular, but is actually exactly equal to a quarter of a circle of radius 4, I'm able to compute the area of this portion of the quarter circle. And I would find the total value of this definite integral by adding the area of the rectangle, which is 12, and the area of the circle, which is 4 pi.